Hello. This lecture will cover pages 171 through 177 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 8G, AC, Thevenin's Theorem Analysis. We're going to start by looking at two problems in the book, which we looked at before. And the first problem we're going to look at is this one right here. It's Learning Assessment Problem E8.17. And it says use nodal analysis to find V out in the network, and there's the answer up there. What I'd like you to do is I'd like you to use Thevenin's theorem on this circuit, with this being the load resistor, and I want you to find the Thevenin equivalent circuit for that RL. Keep it in mind that you're going to be not finding the Thevenin resistance, you're going to be finding the Thevenin impedance. You're going to find impedance out here for for a Thevenin value for maximum power transfer. But at first, what you're going to do is remove the value of RL, and you're going to Theveninize that circuit for RL. And then you're going to do the same thing down here on this problem. Problem E820. Here's your RL resistor right here. That's your load resistor. You're going to remove that load resistor right here, and you're going to Theveninize that circuit. And you're going to find the value of V out using Thevenin's theorem, and here's your answer on that. Now I'll get you started on both of those problems. On the first problem, this is what you should get for a Thevenin impedance. There's the calculation. I hope you tried this on your own, because it's going to look awful easy when I do it. But notice that circuit doesn't have any dependent sources in it, so you can look back in and just reduce all the sources to zero. And you should see that the Thevenin impedance is 0.597 minus J 0.8 ohms. And on the second problem, you should be able to do it by inspection. Matter of fact, on E820, you should be able to get this answer by inspection for the Thevenin impedance to minus J2 ohms. The third problem we're going to work is going to be a little bit more involved, not a lot, but it's this problem on page 171. I want you to find V out here, with this 1 ohm resistor being the Thevenin load impedance, using Thevenin's theorem. Well, notice when you remove this resistor here, if you have to redraw these circuits, remember, redraw them. If you just can't picture this being open here. But you can't look back in and reduce this to zero and reduce this to zero, because it's a dependent source. You can't do this like you did the first two problems. So you have to calculate Z Thevenin, the Thevenin impedance. We're working with AC problems now. It's equal to the V open circuit voltage out here divided by the short circuit current. When you short this, it's two brief problems. V open circuit is the Thevenin equivalent voltage. So that's half your answer right there, not only in terms of finding the Thevenin impedance, but for finding the Thevenin circuit. And here's the Norton current. I short circuit is nothing more than the Norton current. So the first thing I want to do is I want to find E Thevenin. I want to find this open circuit voltage between this point and this point. That's equal to, all I did was started at this point here. That's a voltage source, so I'm down minus 2 Ix. I'm just on Kirchhoff's current voltage law around this loop here. That's all I'm doing. So I'm at this point. It's the reference point because I want to find the voltage between point A and point B, because I'm removing that resistor. So it's equal to a minus 2 Ix plus this voltage, plus the minus. Well, what is this voltage here? Well, with this open, do you see that the current in the circuit from this source here just is in this loop? It can't go out here because this is open here. So the current goes in this direction. So that current is simply equal to 12 at an angle 0 divided by the sum of these impedances. 2, and the equivalent here is a minus J2, a plus J3, it's a plus J1. It's 2 plus J1. So I can find Ix. I can actually find Ix at this point. But all I'm going to do is take this, I'm going to substitute it into this equation, and I get this. Gone through a little bit of algebra, complex math algebra here. I showed you some of it. I can calculate the open circuit voltage, which is equal to this quantity plus this quantity, and there they are. It's equal to 11.96 at an angle 126.8 degrees, and that's in volts. That open circuit voltage is the Thevenin equivalent voltage. Now all we need to do is find the short circuit current, and then we can go back up and we can finish the value for Z Thevenin. That leads us to the next page. In this case right here, I just short the terminals out, and I want to find this current flowing here. Incidentally, the short circuit current is the current in this branch from this point the whole way down to this point. Keep that in mind. So at point V1, I'm going to use nodal analysis here. At this point V1, by Kirchhoff's current law, I get a plus Ix. Well, that current's defined for us. Minus I2, I labeled that current here. I2 plus to minus through these elements. I mean, you can combine these reactances and just put a J1 ohm inductor in here. But we'll keep them separate here. And then minus the short circuit current, because it's leaving in the direction I gave it here. There's my first level equation. What is Ix? Well, it's 12 minus 2Ix divided by 2. Well, how would I get that? Well, do you see this is shorted, and that's a voltage source. So if that's 0 and you're up a voltage here, 2Ix, that makes this V1 point 2Ix. V1 was a dummy variable because I knew that voltage there. If this is ground and you're up 2Ix, that voltage at that point is 2Ix. That's in volts, though. Don't let that current Ix mess you up. That 2 is going to have to be equal to a dimension such that 2 times Ix gives you volts. So I just make that substitution in down here. I say the current Ix is 12 minus 2Ix divided by 2. The current I2 is 2Ix divided by a J1, the equivalent of this. I combine those together. They're both reactances. Minus the short circuit current. Well, since Ix is equal to 12 minus 2Ix divided by 2, which we set up here, Ix is the voltage here minus the voltage here divided by 2, I can make a substitution with Ix equal 3 amps, basically, and I end up with a short circuit current of 6.71 at an angle of 63.43 amps. Now I can finish my ratio to get our Z Thevenin. I put my open circuit voltage in, I put my short circuit from the previous page, I put my short circuit current in here, and I end up with 1.78 at an angle of 63 point whatever. The scanner, when I scan this, I missed this out here, but you'll have to make sure you make this calculation and can get this. Having impedance in this form doesn't do you any good, with the exception of you can get the impedance angle here. And that impedance angle, remember, is the angle of the voltage minus the angle of the current. So that's an important angle, that impedance angle. That impedance angle, if it's in the first quadrant, it's an inductive circuit. If it's in the fourth quadrant, it's a capacitive circuit. So if this angle is positive, it's an inductive circuit. If this angle is negative, it's a capacitive circuit. We already talked about that. But the usefulness of the impedance, of the phasor impedance, is in rectangular form. I convert this to rectangular form and I can see what the Thevenin equivalent looks like. It's 0.8 plus J 1.6 ohms. It has a 0.8 ohm resistor and then an inductive reactance of 1.6 ohms. So we draw the circuit. And when I asked you for the Thevenin equivalent circuit, you know you have to draw the circuit, and we do that. And when we do it, we get this. There's my Thevenin equivalent voltage. I draw it in. And this right here represents my Thevenin. This represents Z Thevenin, my Thevenin impedance right there. It's complex. Has a real part and imaginary part. So now I can calculate the open circuit voltage in this problem. I just put the 1 ohm back on out here and I use a voltage divider rule. I take the total voltage times this pure resistance divided by the sum of these two. And I did that and I end up with the voltage, the output voltage. The answer to this problem. I'm going to point something out at this point that's very important. I have 2 stars on it. The value of ZL out here, I mean, it was 1 ohm, but what if we had to replace this with a value such that maximum power would get from the source out here? We did maximum power transfer with a pure resistor, but what about when you have a Thevenin impedance that you have to match out here, or you have to have out here for maximum power? I want you to note the value of the load impedance for maximum power transfer has to be the complex conjugate of the Thevenin impedance, because the reactance terms must cancel and leave pure resistance. Complex conjugate means if the Thevenin impedance is 0.8 ohms plus J 1.6, the complex conjugate of that is going to be 0.8 ohms, the real part doesn't change, minus J 1.6. So that's the answer. For maximum power on this problem up here, what's the value of load impedance have to be? It has to be the complex conjugate of the Thevenin impedance. That's what I'm denoting here with this asterisk, which is equal to 0.8 minus J 1.6 ohms. That's the answer for maximum power. That's the value that Z load has to be, the load impedance has to be to get maximum power from here to here. It's just the complex conjugate of what you see up here. And that should make sense thinking back to the first half of the semester. Do you see that if this Z Thevenin here is 0.8 minus J 1.6, the plus J 1.6 inductive reactance will cancel with the minus J 1.6 capacitive reactance. They cancel and you get pure resistance matches, which is what you have to have for maximum power transfer. All you're doing is canceling out the reactance up here. So, what about if you have this problem right here? I think I made a little extra problem. See if I can't find it. I guess you could just look at that. It's pretty easy to see. I said here, let's say we have a Thevenin equivalent circuit looks like this. We have some E Thevenin that we didn't calculate, but here's my Thevenin impedance, 8 minus J8. It's a capacitor. It's a capacitive reactance. I Theveninize a circuit and I get this. And I put a load resistor. What's the value of R have to be, Z sub L, the Thevenin impedance of the load have to be, or what's the value of the load impedance have to be for maximum power transfer from here to here? It's the complex conjugate of this. Here's the answer. The load impedance for maximum power transfer out here has to be equal to the complex conjugate of the Thevenin impedance, which is going to be 10 plus J8 ohms. This plus J8 has to cancel the minus J8 if you put it in out here, and it leaves pure resistance matching, 10 ohms to 10 ohms. It's an important concept. And then finally, I want to take a look at problem on page 174. Example problem. Find the Thevenin equivalent circuit for the load resistor RL in the following circuit. Here we have a circuit, and you might see this circuit in a future class. I mean, it could be a model of some active device. And you just want to Theveninize this circuit for RL out here. Okay. And we have phasors. We have a phasor current out here, and we have a phasor voltage here, then, therefore. But there's no impedance. There's no reactive terms in here, so the impedance in this circuit is purely going to be resistive. So I want you to notice, remove an RL, and I want you to look in there, and I want you to recognize that you can't just short this out and open this and say, oh, the Thevenin resistance is R. Because there's a short, that's open, so it's just R. It just sees R. You can't do that because that is a dependent source. You know you have to find R Thevenin by finding the open circuit voltage divided by the short circuit current. So I want you just to stop the video, look at this, and see if you can't work this out. I took my time here. I did not break any rules. And I worked through this problem, and I ended up with the Thevenin equivalent circuit here. Notice that the Thevenin voltage, Thevenin phasor voltage in the frequency domain is going to be equal to I times R times the quantity 1 plus mu. And up here, the Thevenin resistance is R times the quantity 1 plus mu. And I put my load resistor back on. Now, if you know that's a general equation for the model, that's a general circuit for the model of that active device up here for different load resistors. If you know the current I, the value R, and a mu for a particular type of active device, you can calculate either the load voltage or the load current for different loads. For 100 ohms, for 1K, for 10K. It makes it a very simple series circuit problem, as opposed to doing this for 4 different resistance values up here. Incidentally, one student may do it this way. Another student might say, well, before I analyze this circuit, I'm going to convert this current Norton equivalent to a Thevenin circuit on its own. So you can replace everything to the left of my pencil with a Thevenin voltage and a Thevenin resistance. Just move this R up here and replace this with a Thevenin voltage of I times R. And you can work the problem. You're going to get the same, you'll get the same solution. Maybe it's easier to see it that way. That's not breaking any rules. This may be more difficult for people to see. Maybe if you rewrite this in terms of Thevenin equivalent, and then you Theveninize that complete circuit, it might work out easier for you. And that concludes this lecture and the chapter.